Hello, I'm Seema and welcome to part 3 of the chapter Hydrocarbons. In part 1, when I did the introduction, I gave you a broad classification of hydrocarbons. And I told you that hydrocarbons can be classified as saturated and unsaturated. And saturated hydrocarbons are known as alkanes and cycloalkanes. Unsaturated are known as alkenes and alkynes. And then there's a third category of hydrocarbons which are known as arenes or aromatic hydrocarbons. So from this video onwards, let us start the study of these different classes separately. So the first class of hydrocarbons are alkanes. And let us begin our study of alkanes. The first member or the smallest hydrocarbon that you can have would be a compound of hydrocarbons are compounds of carbon and hydrogen. So a compound that has one carbon atom. And if it has one carbon atom, since carbon has a valency of 4, it must form bonds with 4 hydrogens to form the smallest hydrocarbon, which is saturated because all bonds are single bonds, and therefore it is a saturated hydrocarbon. It is an alkane. And the first member is methane. Since methane is found in marshy areas, it is also known as marsh gas. It is also found in coal mines. And do you know that the cattle, even in their gut, you have methane? When you kind of store their food in their in a special bag, and then they chew their cud, that is when a little bit of marsh gas is produced in their gut also. So methane is therefore, because it is found in marshy areas, it is also known as marsh gas. The word alkane, or rather alkanes, are also called paraffins. Paraffins is a Latin term, and it means para means little and affin is for affinity. So paraffin is little affinity, compounds that have little affinity. What is affinity? Affinity is love or chances of merging with something else. Affinity, attraction. So they do not have a tendency to react with others. They have a tendency to just be by themselves, because it is understandable, the valencies are satisfied of all the atoms and the compounds are saturated. There are no more bonds that can be formed. So what could they expect? They have everything. All their bonds are single bonds. Every atom is at maximum distance from each other. So they form stable structures. That is why they do not usually react much. And that's the reason why they are called paraffins, or compounds that have little affinity. Now, let us take methane. Methane is CH4. If you replace one of the hydrogens with carbon and then satisfy the valency of that carbon with hydrogens, then let us say that this was the original carbon and this hydrogen has been replaced by a carbon here. If it has been replaced by a carbon, it forms one bond with this carbon, but it has a valency of 4, therefore it will form 3 more bonds with 3 different hydrogens. Thus, this carbon is also now forming 4 bonds, and this carbon already was forming 4 bonds. Each carbon forms 4 bonds and each hydrogen forms a single bond. So this results in the formation of the second member of alkanes, which is ethane, right? And if you remove this hydrogen and replace it with a carbon, then you will get the third hydrocarbon, which will be, if you replace this, then this will be a carbon. So you'll have hydrogen, hydrogen, hydrogen with that carbon. So you have CH3 here, and this remains only CH2 because this hydrogen is also turned into carbon. So you'll have CH2 and CH3 in the end. So this is the third member, which is known as propane. And if you go on increasing, substituting one hydrogen of the last carbon, you get to the next member of the homologous series. But there is one very interesting phenomena that you observe when you come to the fourth member, but I'll come to that later. And that's the reason why I wrote only 3 here. Let us first talk of what is the structure of methane like, or what is the structure of these hydrocarbons like. In hydrocarbons, carbon has sp3 hybridization, which means 1 s orbital and 3 p orbitals of the second shell. They redistribute their energies and they become identical orbitals. and then they form a structure. For the 4 bonds, the carbon is in the center and the 4 bonds are at equal distance spatially from each other. It is not in 2 dimensions, it is in 3 dimensions. Imagine I am here, I have 4 limbs, and these 4 limbs have to be at maximum distance from each other. How would it happen? What would be the best arrangement? It would be if one limb goes up here, one limb is here, one is there, one is there. So I'm forming a kind of a triangle in the bottom, and then the center, the carbon is in the center, and one limb goes up. In that way, all angles between the different bonds are 109 degrees 28 minutes. And that results in the formation of a tetrahedral structure. Imagine that this is a triangle in the bottom. Okay, this triangle is in the bottom, and you can now imagine that the tips of this pen, okay, these tips are hydrogens. Imagine these 3 tips to be on the 3 corners of this triangle. Okay, you can imagine this, isn't it? You can imagine that the tips are on the 3 corners of the triangle. Now, where my fist is, that is where the carbon is, or where these 3 are joining, that is where the carbon is. And these are hydrogen atoms, and the pens are bonds. Then, the 4th bond will be on top here. So the 4th bond is on top here. So if you look at it from any direction, you will get the same structure. It is a 3-dimensional symmetrical structure. All angles are the same. If you will see, it will appear to be the same structure in all directions. That is the structure. It is known as the tetrahedron. Now, if you join these lines, join this, make this a triangle here, okay, and then join the lines of all the ends. And what will you see? If you make a structure like that, and make walls along every side, you will get a tetrahedron, a shape of a tetrahedron. That is why we call it a tetrahedral arrangement. A body which has 4 heads and which is symmetrical. So you get a tetrahedral arrangement. So according to the Vesper theory, that is valence shell electron pair repulsion theory, according to which each bond is a pair of electrons, or even if it was a lone pair of electrons, in this case they are all proper bonds. Each pair of electrons, they repel each other. Electron pair repulsion. Each bond is an electron pair. It repels the other electron pairs equally. And since they are all CH bonds, the energy of every bond is the same. So they repel the other bonds with the same energy. So the best, most stable arrangement will be if all of them occupy the same distance from the other bonds. And that is possible in the tetrahedral arrangement. Now, that is methane. How did we prepare ethane? We said, let us change one of the hydrogens with carbon. We changed this hydrogen with carbon. So let us imagine that we changed this hydrogen with carbon. Let the pink cap now be carbon, a carbon atom. If it is carbon atom, these 3 hydrogens remain with this carbon, but this carbon will now have 3 more hydrogens on this side. So that will result in the formation of ethane. 3 hydrogens here and 3 hydrogens here, 2 carbons, C2H6, right? And then imagine that the next carbon, when you do this, one of these hydrogens has turned into carbon. Then that structure will go further. It will form the same thing, extension of the same thing will happen. And you will find that the chain grows longer and longer, and the next member of the homologous series is created. And that is how you can imagine the 3-dimensional structure, how the structure would be formed. And while you are doing this, you will also understand that any of these hydrogens could have been turned into a carbon, and therefore the structure would move in a different direction depending on which hydrogen is being replaced by a carbon. And then you could rotate it and it becomes symmetrical. But then there is a variety that is possible after the 3rd member, which we'll understand now when we do isomerism. But basically we understand that every carbon is sp3 hybridized, but if you look at every carbon atom which is there in the chain, every carbon is going to form this tetrahedral arrangement, whether it is with other carbon atom or with hydrogens, but the arrangement is always going to be tetrahedral in saturated alkanes. Right? If they are all single bonds, it has to be a tetrahedral arrangement. So now let us come to the fourth member. And the fourth member is butane. So, in the case of propane, you notice that you get the 3 carbons in sequence. There is no other possibility. 3 carbons have to be in one line. But if you had 4 carbons, let us replace one of the hydrogens here, and then I'll get a compound, that is, I'll get butane. So let me do the same thing that I have done to get propane. So this becomes CH3, and this carbon now becomes CH2, this remains CH2, and this is CH3. So this becomes butane. But this butane is a straight chain. There is also a possibility. Who said that only the hydrogen of the last carbon can change? How about the hydrogen of this carbon? Imagine one of the hydrogens of this carbon is removed and gets attached to a carbon. Then also you will get butane. So let's do that. You will get, let's write this. You have CH3, you have CH here because one of these hydrogens is connecting with carbon, and you'll have CH3 here, and this is the one that branched out and got connected with carbon. And this carbon will further form 3 bonds. So now the branches, instead of the 3 carbon with 3 hydrogens on that side increasing the length of the chain has become branched, and you'll get these 3 hydrogens like this, right? And just to avoid using so much space, I'll write CH3 here, right? So you'll get, this is now, what is this? You have done nomenclature. This is 2-methyl propane, right? This is 2-methyl propane. But if you write the molecular formulae of both of these, butane and 2-methyl propane, what is the formula of this? This is C4H10. This is also C4H10. They have the same molecular formula, but they have different structural formulae. You noticed? They both have the same molecular formula, but they have different structures or different structural formulae. Such compounds which have the same molecular formula, but they have different properties because they have different structures, are known as isomers. This phenomenon is known as isomerism. Isomerism is when compounds have the same molecular formula, they arrange differently to give you different molecules. And therefore they act as different compounds and they have different properties. So we'll say butane shows isomerism. Propane cannot show isomerism because there is only 2 terminal carbons and 1 carbon in the middle. So, or rather, when ethane expanded to propane, the hydrogens of either of the 2 carbons would have, one of the hydrogens either on this carbon or this carbon would have got connected to carbon. So it would only have led to an extension of chain. A branch cannot form. A branch can only be formed after you have 3 atoms. Then a branch can come out from the middle. If you have the tip and the bottom, branch can only come out from the middle. So there should be a carbon in the middle which allows a hydrogen to be substituted with carbon. So you get 2 isomers. So we see isomerism in alkanes, and we have noticed that when the molecular formula is the same and the structures are different, we call it structural isomerism, right? Now structural isomerism, or in the case of alkanes, we see position isomerism. How position? The position of this methyl group, instead of the methyl group coming to the end, the methyl group has attached itself to the second carbon. So its position is different, due to which the structure is different. So they show position isomerism and structural isomerism. There is a subtle difference between the two. Let me explain the next example and then I'll show you these two. So this was butane. Let's come to the next member now, pentane. The first member we'll make in the same way, the first isomer that we'll be making will be extension of the chain. So we'll imagine that one of these hydrogens is replaced. So you'll get the CH3 here, this carbon now becomes CH2, this is CH2, this is already CH2, and this is CH3. So I get pentane. Pentane is the next member. Now, if you get pentane, which is the next member, let us imagine that this methyl group, it's not necessary that it is the first carbon that extends. In the case of butane, you have these two options, right? You have two options. These carbons could also be branching out. So let us write down. The next pentane would have another structure. It could be, or this molecule could have different structures. How? You could imagine that it's not necessary that pentane is formed from this only. Pentane could have been formed from here also. And if that was the case, then imagine this carbon got, one of the hydrogens was replaced. So you'll get CH3 and this would become CH2 and the rest of the molecule remains the same. CH3, CH3. This is also pentane, right? But what is it? If you give it the IUPAC nomenclature, it would be 2-methyl butane. So this would be 2-methyl butane, right? And now imagine that it's not necessary. If we imagine that here, if we took this and the methyl group that added did not add here, it was not an extension of this, rather it came as a branch of one of these, even then you would have got one of these structures, right? In either case, if it was a branching here instead of this carbon, if it was a branching here, I would have counted from this direction, I would still call it 2-methyl butane, right? So now, what is the next structure that is possible? The next structure that is possible is that you have CH3 here, you have carbon here, and the substitution is taking place on this hydrogen. So you get a methyl here, you get a methyl here, and a methyl here. This is also pentane because it has 5 carbons. But if you give it the common nomenclature, it is still pentane. But I will not go into the details of nomenclature. I'll do a separate video, therefore I'm not going into the common nomenclature. But according to IUPAC nomenclature, this would be 2,2-dimethyl propane. This will be 2,2-dimethyl propane. So we see that pentane has 3 isomers, right? Pentane has 3 isomers, and these 3 isomers are normal pentane, 2-methyl pentane, and 2,2-dimethyl pentane, where branching is increasing. And as you go to the next member and the next member, you will be able to make more and more structures that show isomerism. Let us now make the structures of hexane also. But before I do the structures of the isomers of hexane, let me come back to this. You notice that there are 2 structural isomers of butane and there are 3 structural isomers of pentane. And the difference between them in these cases is due to their position, the position where the methyl groups attach themselves. Therefore, this one shows a difference because of the position. The structure, of course, is all of them are structural isomers. But here, the structure is different because of the position of the methyl group. Here you see the difference in the change in the position of the methyl group is giving rise to a new isomer. Therefore, they are known as position isomers, right? And of course, all of them are structural isomers. So let us now take the next member, that is hexane, and let's try to make all isomers of hexane before I wrap up this video. So, hexane, let us just now not go into deriving, let us make a 6-carbon chain. CH3, CH2, 3, 4, 5, and 6. So this is hexane. The first member, straight chain. Let us now start branching it. let us start playing with the carbon atoms and start making. It is such fun to write down the isomeric structures. Yeah, once I'll be doing the isomers of hexane, I would encourage you to try making isomers of heptane and octane too. You're going to have real fun with it. Why? Because you'll notice that sometimes you think you made a new structure, and when you count from the other side while naming it, it happens to be the same compound. So let us first make one branch. So if we have one branch, our chain will be of 5 carbons now, right? So branch cannot be on the last carbon. So 1, 2, 3, 4, 5, right? Branch has to be, so we can have a branch on either of these 3 carbons, a single branch. So you can have one isomer with a branch here. So if there's a branch, 3 bonds, it needs 1 hydrogen, 2 bonds needs 2 hydrogens, 2 bonds needs 2 hydrogens. And if you always see the molecular formula, if you keep count of the number of bonds, you'll always come to the right formula. Then now, I told you that we have options of these 3. Imagine that this methyl, let us name this compound. This is hexane. This is 2-methyl pentane, right? Imagine that the methyl group was on this carbon. Then what would the name of the compound be? Then the name of the compound would still be 2-methyl pentane. It is only that I would start counting from this direction. It is like, imagine that I'm looking at this compound from the front of the board. It is, this seems to be the 4th carbon. If I go back behind the board and I look, then this is the 2nd carbon. If I'm looking at this compound from behind the board, this would be the 2nd carbon. You always count from that direction where you get the lowest locant. I would encourage you to do the nomenclature that we've done in the previous chapter, and I'm assuming you know it. So according to the lowest locant rule, both the isomers will be the same compound, so they would not be isomers, it is the same compound. So the only other isomer possible with a single branch would be one where you have a branch on the 3rd carbon. So we'll say CH3, CH2, this becomes CH, and you get the methyl group here. This becomes CH2 and CH3. So what is the compound that you got? You got 3-methyl pentane. Okay, so this is the maximum number of branches, single branch that can come. So can we deviate now? Instead of 1 branch, let us make 2 branches. We have the chain that is long enough to allow us 2 branches. So let us take another CH3 and make branches out of it. So if we make branches again, now we'll have branches at 2 places and our chain will become 4 carbon long. 1, 2, 3, 4. And we can have 2 branches. So let us have 1 branch, 1 methyl group here, 1 methyl group here. Fill up hydrogens. This will have 3 hydrogens. This has 3 bonds, 1 hydrogen, 3 bonds, 1 hydrogen, 1 bond, 3 hydrogens. I would encourage you to count the number of hydrogens in each case. You will know, if you keep in mind the number of bonds, you will always get the same formula and the correct formula. So in the case of hexane, hexane is C6H14, right? In all of these, you will get 14, hydrogens will be 14 if you count them. So these were 2 branches. Name this now. This would be 2, 3 dimethyl butane. Right? 2,3 dimethyl butane. And imagine that the methyl group, both the methyl groups were forming branches on the same carbon. Then what is the compound that I'd get? CH3 here. Let us imagine that this is the carbon that has both the branches. So CH3, CH3, CH2, CH3. Do you see? Now this carbon is forming 4 bonds with 4 different carbon atoms. Right? It is forming 4 different bonds with 4 different carbon atoms. So give it the IUPAC nomenclature. This would be 2,2-dimethyl butane. Now, are there any more isomers possible? Can you make 3 branches? No, you can't, because in order to have 3 branches, there should be 1 other atom. If you made 2 branches here, if you have a branch here, that would, let us say I put this methyl group here, it'll be the same chain, only twisted. A chain, whether it is straight or its head is bent, makes no, it is the same chain. So the chain is only extending downwards, it's not a branch. For a branch, it has to be a carbon which is not the last carbon. So these are all the isomers that you would get for hexane. And now your job is to make isomers of heptane and octane and enjoy the game. So with this, I'll wrap up today's video. If you found it helpful, please give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.